Hi everybody, what I will talk today is about semiconductor devices with other two group mates. Before we go to the details of semiconductor, let's quickly go through the historical background of semiconductor devices. The forward step on innovation of semiconductor in general, or to be specific on transistor, was done by William Shockley in 1945 at the Bell Lab. So William Shockley put forward concept on semiconductor amplifier operating by means of field effect principle. The whole idea was that the application of a transverse electric field will change the conductance of a semiconducting layer. Unfortunately, this principle was not supported by experiment, and later, after 2 years, in 1947, John Barden and Walter Brittain built a germanium point contact transistor, and this leads to revolutionized the communication industry and computer technology. So let's see why semiconductor devices are important, or how do we study them. There are two important things with semiconductor devices. The first one is the rectification. So if you apply to semiconductor devices a signal that have positive and negative, they have the ability to rectify the signal, and this is the foundation for modern electronics. And the second important feature of semiconductor devices is that they are sensitive to light. That's also the application we see on PV cells. So these two importance of semiconductor has changed the technology advancement of the world beyond anything can be imagined. So we should really understand the PN, or the semiconductor physics. So at the beginning we have P and N type of material. So when we say P type of material, we mean that it only contains holes. That means deficiency of electron in the lattice, which can act like positive charge. And when we have the N material, it means it contains only electrons. So what exactly this means is, or how do we create P and N material, is that by the concept called doping. So by doping, we mean that we intentionally introduce impurities to the pure semiconductor. Like if we have silicon, for example, we introduce some impurities. For example, when we create P material have extra holes, so we dope silicon with elements like phosphorus. And when we create N material as well, we dope silicon with boron. So that's how we create the P and N materials. So now we have the P and N materials, and we make a junction. That means we bring both of them to form a contact. So when we form this contact, what happens is electrons will diffuse to the left and holes will diffuse to the right and make a depletion region. And this depletion region have a contact potential which varies from 0.1 to 1 volt. So let's try to look also more into detail the PN junction from energy band point of view. And this is how the PN junction looks like from energy band point of view. So the above one is the conduction band and the lower one is the valency band. Due to charge transfer, the energy of the P side is higher than the N side. That the P side has acquired negative charges. So given the contact potential, which I explained before, which varies from 0.1 to which varies from So the contact potential varies from 0.1 to 1 volt. So as a result, now we have four types of different fluxes, as we can see from the figure. If we see from the conduction band, we have two fluxes, and the valency band, we have two fluxes. If we see at the electrons that's at the conduction band, we have the recombination flux which flows from the n side to p side due to the large electron concentration on the n side. And on the opposite side, we have also a generation flux which flows from the p side to n side due to the generation and subsequent sweeping of electron by the junction field. If both fluxes are constant, if both fluxes have the same magnitude, we call it's in the equilibrium. And when we see also on the valency band, we have two types of fluxes, the same idea from the electron point of view. So we have recombination flux from p to n side, and we have generation flux from p to n side. So equilibrium will reach if those two fluxes are equal. And next, let's see a forward bias configuration. A forward bias configuration is achieved when we connect the p side with positive potential and the n side with negative potential. So what happens is the convectional current flows from the positive potential and the electron flows from the negative point of the applied potential. And the electric field, due to the depletion region denoted by E0, is towards the left side, and the electric potential due to the applied electric potential is to the right one. So the total electric field will be EF minus E0 because they have different direction, and the total applied potential will be the difference between the depletion region and VF. So the applied voltage, the total voltage will be the difference. So this one, if we try to understand this from energy band point of view, the applied potential will result in stepping up the bands on n side. So this one will make the diffusion more quickly. So what we see here is the n side raises by EV0, and the recombination flux is increased by E, the exponential function here, and this exponential function is assuming that the electron obeys the Maxwell-Boltzmann assumption. So the electrical current flows from P to N side, and the electrical currents due to the electron flow, which I denoted by IN, will be the difference of the two fluxes, and the electrical current due to the hole will be the difference between those two fluxes. And we can substitute these numbers and factor out the common one, and we get like this. And the total current will be due to the summation of the IN, the current due to the electron, and the current due to the proton. So if we substitute this and simplify stuff, we get at the total current is equals to I0 times the exponential function. So from this equation, we get a relation between the current and the potential. And if we draw this relationship, we got the VI characteristics. So the first quadrant represents the forward bias, and the third quadrant represents the reverse bias. So in the forward bias, we observe that as we increase the potential, the current will be linear at the beginning and it goes exponential. And let's see what will happen on the third quadrant. So the third quadrant is the reverse biased. So what we mean by reverse biased is that the N side is connected to positive potential and the P side is connected to the negative potential. So the electric field due to the depletion region will be to the left, and the electric field due to the applied electric potential will be also to the left. So both of them, they will be added, and the total applied voltage will be also the sum of those two, to put the contact potential on the depletion region and the applied potential. So the result, when we see this one from band point of view, they will be added. So the N region will be dropped one. The dotted line is on equilibrium. So if we follow the same derivation from the forward biased, what we get is the total current will have the same as with I naught. So if we go back and see the VI characteristics, in the third quadrant we have a constant relationship, as we can see it here. It will be a constant relation here. But what practically we observe is that at high electric potential there will be a breakdown and the current will start to flow, and this one is what we call it avalanche or Zener breakdown. And I will not go to the detailed calculation of this one, rather I will recommend you this book to read, which gives a nice discussion on avalanche and Zener breakdown. So what we have discussed so far is when we have a P material and N material, when we form a junction. That's what we have discussed so far, is making a junction from two regions. Let's extend our discussion and let's see what will happen if we make two junctions like we have P and P. So the PNP junction, which is called the junction transistor, is formed by connecting two PN junction back to back. So basically what we have now is three regions. So the junction to the left is forward biased and the junction to the right is reverse biased. The forward biased junction is emitter electrode, while the reverse junction is collector electrode, and the N region is in the middle, which is called the base. So what happens here is that the forward bias circuit on the left injects holes across the junction into the base, and the hole diffuse into the base until they are collected by the collector. This is actually where the names emitter and collectors also comes. Like the emitter circuit here emits holes, that's why it's called emitter, and the collector circuits collects the emitted holes, so that's why it's called collector. So now let's extend our discussion and let's see a mathematical derivation on this phenomena. So the emitter circuit is forward biased, so the emitter current can be written like this. We already see it on the forward biasing circuit. So we see that the emitter emits holes and diffuse through the base, and they are collected by the collector junction. But it's not always true that thus all holes diffused by the emitter circuit are collected by the collector. There are some holes that may decay on the way. Suppose the fraction phi represents the number of holes that are decayed. So we can write the collector current as the sum of IC naught, which is very small number, plus alpha times IE. So we introduce alpha It's a fraction. We introduce alpha of those holes which are survived, which are successfully diffused from the emitter to the collector. So if we go back and see our circuit, we have a load here, RL, and the potential on this load is IC times RL. That's what I have written here. So I represented IC with alpha times IE. So to see that how the input signal is amplified or have a gain on the output signal is to make a derivation on to derive the load voltage with meter voltage. So this is the load voltage, and if we substitute IE from this equation, we have a relation between IL and VE. So we derive VL by VE to see how the emitter circuit leads to an increment in the load, and to see on the power side we derive power is voltage times current. So we substitute that one in the above equations and we derive the power by PE, and we get the same two things. So let's consider to have a physical insight. Let's consider a so let's consider IE of 10 milliampere and kVt over E. Let's consider at room temperature, it will reduce to 0.025, and let's consider RL of 2 kilo ohm. So if you substitute those values in the previous two equations, in this equation and this equation, we got a voltage gain of 800 and a power gain of 200. This is fascinating because we don't do any complex circuit or any fancy controls. We only build this PN junction, and we got a voltage gain of 800 and a power gain of 200. And this is the basic principle behind amplifiers and microphones. We are raising the power, just the level of the signal by 800 times and 200 times. Thanks, and Jimmy can continue now.
Buddy, what I'm going to talk about today is semiconductor devices, specifically applications to the tunnel diode and the gun diode. So if we look at the tunnel diode, it was invented by Isaki in 1958, and in terms of applications for these devices, it could function as an oscillator or as an amplifier, and I'll explain both of those later. And the frequency range that these devices operate in are between 300 megahertz and 300 gigahertz. So if we look at the band structure or the band levels for a PN junction, we see the conduction and valence bands for the P and N region, and they're offset by a distinct value. And in the junction, there's a depletion region. And if we go to extremely high doping levels, then this depletion region decreases in its width. And the electric field across this width is given by the contact potential divided by the width. And for these very high doping cases, the electric field is very high. And this results in a drastic shift of the band structures, as seen on the bottom right. So if we look at the case of the tunnel diode in its equilibrium state, there's no voltage being applied, and so no current is flowing. And with the case of a very high doped material, such as the tunnel diode, you actually have the Fermi energy level crossing into the conduction band for the N-type region. Now, there's no charge flow in this state because all of the electrons are in their lowest energy state. But if we go to a reverse bias where the electric field is traveling to the left, the electrons want to move to the right. When this reverse bias is applied, the N bands shift downwards, and therefore the electrons in the valence band in the P region can tunnel across this boundary and enter into a lower energy state in the conduction band of the N region. And then once they are in the N region conduction band, they're allowed to conduct freely. And so a very small current or a very small voltage in the reverse bias case produces a high current. So that's shown by this graph at the bottom. Now, when we go to a forward bias, the N region or the N type shifts upwards, and so the electrons in the conduction band of the N region can move into the valence band for the P region. And so this results in an increase in the current as a function of voltage. But eventually, this valence band ends up getting filled up rapidly. And as you increase the forward bias even more, the bands begin to not overlap. So they're not crossing anymore. And so this results in a decrease in the current as you increase the voltage. So then what you're left with is this region where the current actually decreases with an increase in the voltage. And this region is known as the negative differential conductivity zone. And all of this tunneling is made possible by quantum effects. So I'd like to discuss that now. So the tunneling is made possible because the wave function penetrates a finite potential barrier. And we've actually seen this before in some of our homework assignments for the semester. So if you consider an infinite potential well here, let's just consider the energy state n equals 0, nothing higher. You see that the wave function does not penetrate this infinite potential walls, and the value of the wave function at the boundaries are 0. If we square the wave function, that gives us the probability of finding the electron in a specific location. And inside of these infinite potential boundaries, the probability of finding the electron is 0. However, if we decrease this potential barrier to lower than infinity, let's say just the constant V0, then the wave function is allowed to penetrate this potential barrier. If we square the wave function in this case, then we have a finite probability of finding the electron in this potential boundary. And there's actually an error at the bottom. That shouldn't say infinite potential boundary. It should say finite potential boundary. So if we look at the case of a standard doped p-n junction, we can assume that the electrons in the p region and in the n region, if we look at them as isolated cases, then it's like the electrons are in a particle in a box, let's say. And the depletion zone can be looked at as the potential barrier that blocks the electron from traveling across. Now, with a standard doping, this potential boundary is very wide. So even though the wave function is penetrating the wall, it's not allowed to cross. But if we have a very high doping concentration, then this potential barrier decreases in its width, and then the wave functions are allowed to cross. And when they cross, you have a higher than zero probability of finding the electron in that zone. So in this case, you're allowing tunneling to happen. So the probability is greater than zero. So in terms of applications for the tunnel diode, the first one is that it can be used as an amplifier. So we know that from Ohm's law, the current is equal to the voltage divided by the resistance. And we see that the resistance in the NDC region is negative. So what that means is that the current actually travels in the opposite direction of the applied field. So if you took a signal, say one shown at the bottom of the screen, and applied it to a current element containing NDC type behavior, then what will happen is current will actually flow towards the signal, and power is actually absorbed by the signal because power is equal to the current times the voltage. And this power amplifies that input signal and causes the signal to increase or amplify. The second application of the tunnel diode is an oscillator. So what we can do in this case is we can add a resistor to the circuit in series with the tunnel diode, and this resistance will be equal and opposite to the resistance of the tunnel diode. So then what you have is the resistance of this circuit as a function of voltage, or the slope, is 0 for a finite voltage interval, shown at the bottom right of your screen. So if you're operating the tunnel diode in this form, then the signal in that finite voltage region will oscillate back and forth forever, in theory. And so these are used for quartz crystal oscillators, oscilloscopes, LC circuits, and antennas. And they operate in the microwave range, which is 300 megahertz to 300 gigahertz. Next, I'll move on to the gun diode. So this also operates on the principle of negative differential conductivity, and it's the result of it operates as a result of the electron transfer from high mobility, low energy states to low mobility, high energy states, and I'll explain what that means. Also, the gun diode is a bulk property of the homogeneous material. It doesn't require any PN junctions like in the previous tunnel diode case, or any other nanoscale manipulation of the surface. So it's a bulk property. And lastly, even though it's called a gun diode, it's really not the correct term because it can operate in both directions equally well. So first, let's consider what the band structure or the E versus K diagram looks like for typical gun diode materials, usually gallium arsenide. They consist of a central valley and a secondary valley, and the secondary valley is 0.36 electron volts higher than the central valley's 0K state. So one other thing about this secondary valley is that if an electron passes into the secondary valley, the mobility of that electron will be 50 times lower than that of an electron in the central valley. So this is very important for the gun diode. So in order for an electron to jump from the central valley to the secondary valley, it needs to have at least 0.36 electron volts of energy. So this can be seen on the current density versus electric field plot on the right. Once you pass a certain electric field, enough energy is given to the electron where it jumps into the secondary valley, and the mobility of those electrons are lower, so then you have a reduction in the current. And also this only exists in, or not, I shouldn't say only, it exists in gallium arsenide, but not in other semiconductor materials such as silicon and germanium, and that's due to a different band structure. So now I'd like to go over the principles of operation for these gun diode materials. So let's assume that we apply an electric field across a gun diode material, let's say gallium arsenide. Next, we'll assume that this electric field that we apply is higher than the threshold to bump some electrons up into the secondary valley. Third, we'll also make an assumption that there's very small variations in the doping concentration as a function of the distance across this material. And this is actually very critical to the gun diode operation. So if we make that assumption, there is actually an increase in the electric field locally at the point where the carrier or the charge carrier concentration is changing as a function of position. And this electric field increase is listed or labeled as E domain, so EDOM. If we look at that on the current density versus electric field plot, it's shown there in the middle of the screen. So if we apply the electric field to this material, the electric field would be going towards the left, but that means the electron motion will want to be towards the right. Now, the electrons will start to move in the direction towards the right, but we know that the electrons at this boundary are very slow because they've jumped up into the secondary valley, and the electrons behind them are traveling fast because they are not in the secondary valley. So what this results in is a charge accumulation at the boundary, and then as a function of time you have an increase in the charge accumulation, and the boundary moves slowly, and eventually this boundary reaches the end of the material, and the speed at which this travels, or the frequency at which this oscillates across the material, is equal to the drift velocity of the electrons divided by the length of your material. And this behavior will actually go from left to right, and then back to the left, back to the right, and over again. So there are some considerations for operation that must be met. So the first one is, let's consider when we apply this electric field across our sample, the electric field is equal to the voltage that we apply across our sample divided by the sample's length. And if we rearrange the variables, we know that the voltage is equal to the electric field times the length of the sample. So we also know that the electric field, there's two different values there. There's an electric field that is the average electric field across the material, but there's also the slightly higher electric field across the very thin domain thickness. And so the thickness of that domain is given by W. So everywhere not in the domain is given by L minus W. So if we plug in typical values for gallium arsenide, then we get W equal to about 40 micrometers. So that's how wide this domain interface layer is, where the charge concentration is varying, and the total length of the material is usually about 200 micrometers. So what does this mean in terms of the device operation? Well, if the material is larger than 200 micrometers long, then it becomes very noisy, because then multiple domains will form, and that's not good. So manufacturers will usually keep it to around 200 micrometers maximum. The second consideration for these materials is related to charge accumulation. So in order for charge to accumulate at this domain boundary, the charge accumulation as a function of time is equal to the charge at 0 time multiplied by the exponential of minus time over tau. And this expression, tau, is given by the dielectric constant over the conductivity of the material. And so if we look at this, the only way that the charge will accumulate, or charge accumulation as a function of time increasing, the only way that's going to happen is if the quantity e to the minus t over tau, if that is greater than 1. And that only happens when that expression is greater than 1. So if we look at the bottom left of the screen, we have T times the conductivity divided by the dielectric constant. Now, we know that the frequency of operation in the last slide was equal to the drift velocity divided by the length. So that means the time to get across, for the domain to go across the sample, is equal to L divided by the drift velocity. So we plug that in for time, and then we evaluate this expression. Now we also know that sigma, which is conductivity, is equal to the number of charge carriers times the charge of an electron, and then multiplied by the mobility, and this is the average mobility. So there's the mobility of the electrons in the secondary valley, and then the mobility of electrons in the center valley. So if we rearrange variables so that all material constants are on the right-hand side and things that we can change are on the left-hand side, we get the charge carriers multiplied by the length of the sample has to be greater than this quantity on the right in order for the charge accumulation to happen. And so how can we change this? Well, we can't really change the length, because if we make the length bigger, then it'll become very noisy. So the only thing we can really change is the number of charge carriers. So that means that we have to dope our material more heavily in order to operate. Now there's a couple more modes of operation. One of them is actually if you do not have charge accumulation at the domain boundary, but I'll leave that as an exercise for homework. All right, thank you.
Hello everyone. Continue James' presentation, I'm going to introduce more semiconductor devices. The first semiconductor device I will introduce is semiconductor laser. To illustrate the principle of laser generator, let's consider there's a box with gas, and then we can just focus on two of the excited energy level. I mean the first two excited energy levels, the lower energy level E1 and higher energy level E2. Then let's see two simultaneous processes, the absorption and emission process. Assume there's a signal with frequency omega is passed through the gas. Then the photons from the signal are strongly absorbed by the electrons of gas. The absorbed energy makes the electrons transfer from the lower energy level E1 to higher energy level E2. During this process, the signal is definitely weakened because the energy of signal is absorbed by the gas. But there's another simultaneous process, the stimulated emission. Actually, the signal will not only help electrons transfer from lower energy level E1 to higher energy level E2, it also stimulates the electron transfer from higher energy level E2 to lower energy level E1. During this process, a photon with frequency omega is emitted. Here, the omega is equal to delta E over h bar, where delta E is equal to E2 minus E1. Actually, it's difficult to explain the stimulated emission classically, but quantum mechanically it appears on the same footing as absorption process. And these two processes, the absorption and the emission process, have the same probabilities of occurring. However, the stimulated emission process will not directly generate the laser, unless the intensity of emission is larger than intensity of absorption. As we know, for most of materials, the lower energy level always has larger population, which makes N1 is larger than N2. When N1 is larger than N2, we have this equation for the final intensity of the signal. The final intensity I is equal to I naught times e to the minus alpha times L, where I naught is the initial intensity and alpha is the absorption coefficient. If N2 is larger than N1, alpha is negative. From the reuse the same equation, we can see that the I naught is larger than I, which means the signal is amplified. Here we have laser. So to generate laser, the higher energy level should have larger population than the lower energy level. To satisfy this situation, we can pump the gas with a strong beam which excites many electrons from lower energy level E1 to higher energy level E2 to make N2 is larger than N1. Then the laser is generated. Now let's see semiconductor laser again. Actually, for semiconductor laser, we have the similar idea. Remember the p-n junction. If we forward bias the p-n junction, the carriers will distribute in both of valence band and also conduction band. This distribution can make N2 larger than N1. When a signal is passed through the forward biased semiconductor, more electrons from valence band will go to conduction band, as the first picture showed. And this process will emit the photon with a frequency of omega, with the energy of h bar times omega. The schematic of this process is shown in the last figure. Here is a notation. Only direct gap semiconductor can be used as laser generator because for indirect gap semiconductor, the electrons and the holes cannot recombine directly. So the indirect gap semiconductor cannot be used as laser generator. Okay, that's all for semiconductor laser. Next, I will introduce another semiconductor device, the field effect transistor, FET. Field effect transistor is invented by Shockley at 1952. The FET is also the device based on PN junction. Here we will look at the PNP junction as the example, but the NPN junction and any other and more types of field effect transistor are also possible. For PNP junction field effect transistor, the battery is connected across the middle layer, the N layer. And there are three layers. The first is P layer, in the medium is N layer, and at the bottom is P layer. Between two P layers and one N layers, there are two depletion layers. When the battery is connected to the N layer, the current will be generated to flow parallel to N layer's surface. This current is modulated by a transverse electric field established by another battery. This transverse electric field is also called gate voltage. Here from the equation we can see that the thickness of conduction, which is WC, is equal to the thickness of N layer W minus 2 times the thickness of depletion layer's thickness, which one is W naught. The principle of FET is that the depletion layer forms at the junction due to the diffusion of free carriers across the junction. The depletion layers will reduce the width of the conduction layer, the N-type layer, and hence reduce the conductance of the device because the depletion layers does not contribute to the conduction process. And then let's see the effect of transverse field. The gate voltage, the transverse field, is added to the reverse bias the PN junction. The reverse bias will increase the width of depletion layers and also then decrease the width of the channel, the conduction channel. The final result is that the resistivity is increased. Also, we can control the resistivity by adjusting the gate voltage. Now let's consider the drain current versus the drain and source voltage. Let's see these curves. From these curves, we can see that the current will increase at first due to the voltage increasing. But the current gradually stops until it reaches the maximum limitation of the current. The reason is that at high current, the voltage is very large, and then make the region near the drain has more positive charge than the region near the source. Then there is an internal gate voltage of its own, of the field effect transistor itself, which causes the depletion layer to bulge into the channel. Then the current is limited as the highest current level. Here you may have a question whether the channel will vanish if we keep increasing the voltage. The answer is no. Let's assume that what will happen if the channel vanished. When the channel vanishes, the current will definitely vanish too, which makes the the I current is 0. When the current is 0, the voltage, which one is equal to I times R, is also 0. If the voltage is 0, there is no channel narrowing would occur. So these are two contradictory facts. That's why the N channel, the conduction channel, will not vanish. Okay, that's all for field effect transistor. Next, I will introduce more semiconductor device, the microelectronics. It is very similar as the large-scale circuits. In large-scale circuits, we have several circuit elements as resistor, capacitor, and also the power. And here for microscale, we also have the same circuit elements to form an integrated circuit. Those micro circuit elements are microresistor, microcapacitor, and microtransistor. For microresistor, the resistance depends on the doping of the P layer. For microcapacitor, the depletion layer in N region is positively charged, and in P region, the depletion layer is negatively charged. This positive-negative charge distribution will form the capacity of the junction. For microtransistor, we just introduced it in last session, so I will not introduce more in this section. After that, right now, let's consider a combination of a microresistor and a microtransistor. In this picture, the left part is microresistor and the right part is microtransistor. And then here is the problem. We have to insulate these two parts on the same N-type substrate. Otherwise, the circuit will be shorted. But how can we do that? Just remember the biased PN junction again. If we highly positive charge the N-type layer substrate, and then the resistor and the transistor are reverse biased. Then the resistor substrate junction and the transistor substrate junction are both highly reverse biased. So there's only very small current can flow between these two elements, and this small current is negligible. Based on this idea, we can fabricate the whole circuit except the power on the same substrate without circuit short. Okay, that's all for our presentation. Thank you so much.